Hello everyone, my name is Madison Gartner and I'm presenting my forecast project on the changing percentages of unemployed labor force. My data came from the U.S. Census Bureau and covers years 1990 to 2014, a 25-year range. The percentage of those unemployed is an important statistic for businesses to be aware of because it is a significant representation of the economy's well-being. If unemployment is large, it can lead to significant income losses and a large reduction in consumption. As shown by this line chart, the rate of unemployment is rather volatile, taking large increases and decreases over a 25-year period. To gain more information on my time series data, I applied regression analysis. Using the coefficients in this table, I was able to get predicted values of unemployment percentages. After including the predicted values to my line graph, it is clear that the predicted values are the same as the original values trend line. The problem with the predicted forecast is that it does not take into account significant changes in percentages during certain years. Since there are definitely significant differences in the original and predicted values, I conducted an error analysis. There were a combination of positive and negative errors. The positive errors represent over-forecasting, while the negative errors represent under-forecasting. I also conducted square error and absolute error in order to get a mean squared and absolute value. After computing some measurements of forecast errors, I realized that I cannot make any inferences about their meaning until conducting some other kind of predicted values. Therefore, I decided I did decide to conduct a year moving average and exponential smoothing. I was not able to apply seasonality analysis to my data because it is only provided on a yearly basis. After calculating a 6-year moving average, I added this data to my line graph. Although this data does not perfectly match my values, it definitely does a better job taking into account the rise and fall of unemployment percentages than the predicted forecast did. After calculating the year moving average, I calculated the exponential smooth values with a coefficient of 0.1. These values are definitely more accurate than the predicted forecast, but do not have as heavy rises and drops in percentages as the year moving average does. After I conducted some of these error measurements, it appears that the predicted forecast has the best mean error. Year moving average and exponential smooth have higher mean errors, which means that they are undershooting the actual observations. When referring to MAD, exponential smooth has the most attractive value because it is the smallest of the three. All of these models' MAPE values are very similar, but I would say that exponential smooth's value is the best since it is the closest to 10. As we discussed in lecture, a MAP value of 10% is considered very good. Tracking signal does not provide the best determining factor of which model is best because all of these values are between 4 and -4. In order to further see how these values match up with the original data, I added 4 more years to the horizontal axis. It appears that exponential smooth follows the original data the most. It begins to decline in percentage while the moving year average and predicting forecast do not follow the original data at all after these 4 years. After completing this analysis, I believe that exponential smooth provides the best predictor of future unemployment percentages. Although it can be difficult to predict these percentages, I would trust this model the most given its line graph and error statistics. Businesses and economists should use this model in order to make unemployment predictions.